Hello folks, got some fun for you here. A nice starter for a piece of paper. It says factorise these determinants. So this is where you've got to take a common factor out of a row or a column. If you look at it to start with, part A, there isn't any common factors, so you'll have to do a few operations. If you were to do column 1, take column 2, that might give you a common factor. Have a look. So pause the video, have a play with those two. That will keep you out of trouble for a long time. So pause. Now unpaused. Here are the two answers. If you got those, brilliant. If you're clueless and want to have a go again at part B, I'll show you how part A was done. Here's part A. If we did column 1, take column 2, and while I'm at it, I've done column 3, take column 2 as well. You'll then be able to see you could pull out a factor, put that one in brackets there. You could pull out a factor of B minus A. Bit of magic there, it becomes minus 1. You get minus 1, 1, and C. You did the same with this column here by doing column 3, take column 2, you get that minus 1, 1, A pattern again. Right, so you pulled out those two common factors. Looking at this, I then went on to do column 1, take column 3 to get some zeros in it. And that. Good at that point, take C, take A out of that row because it's common to that, sorry, that column, it's common to that column. But I didn't decide to do that. I did a bit of something else. Got another 0 in there, maybe to be helpful later, by doing row 1 plus row 2. And then I pulled out that C take A, and because that becomes a 1 then when you're doing the determinant of a 3 by 3, you use this column to do it. So you cross out that column, do it now. You cross out that column and that thing, and you're left, because that's a 1 now because we've pulled it out here. So you're just left with solving that determinant there of a 2 by 2, which leads to that last factor there. Brilliant. You could have done it a different way, of course, and if you did it a different way and got the same answer, fantastic. If you want to go back and have a go at part B now and see if you can get that answer, I think it's a little bit easier than the other one, but have fun. Right, today then, Matrices Lesson 3, solving linear systems with 3 unknowns. How good is that? Right, we've got to be able to solve simultaneous equations with 3 unknowns using matrices and inverses. To have to an understanding of geometric representation. For interest, we're going to meet the Kramer rule, which can help solve simultaneous equations as long as any number of simultaneous equations, as long as the determinant isn't 0. We'll get to that in a bit. And we're going to practice factorising a matrix and find its determinant. We've done a bit of that already, but we might do more soon. Right, this one, recapping from AS Further Maths. What do you remember from these with Carry On? Well, hopefully, you remember you write it as a matrix, X, where X is just XY, equals B, another matrix. And it leads to this thing over here, if you're not sure about that. How do we get to that? If you got your board. Ooh. All this paperwork. Tell your reports are very boring. Hopefully I'm not doing yours. Right. Oh, no pen. That's about typical. It's usual situation it is. Got my pen. I'll let you stare at that question. You might have done it by the time I found my pen. Oh, then. Right. Here we go. So, what you did with that matrix, if you remember, oops, yeah, you had to do A inverse both sides. Put the A inverse at the the left on both, then that becomes I, so Ix equals A inverse B, and Ix, it's the identity matrix, it leaves things alone, doesn't it? That's how you get to that point there. Okay, this A matrix, if you want this A, what is this A matrix? Well, A equals just the 2, 1, 3, minus 1. Right, so if we're doing A inverse, we're going to find the inverse of a matrix, 1 over its determinant, the determinant of that, minus 2, take 3, which is minus 5. So it's 1 over minus 5, and we swap the matrix around, so you get minus 1, 2, minus 3, and minus 1 there. And then that's matrix B, of course, just 7, 8. And if you take that through, you want to do it by hand. The kids outside. Not got enough maths to do, have they? I don't know if you can hear them screaming. 1 over 5, 1 over 5, 3 over 5, minus 2 over 5, and then the 7, 8. You could do this on a calculator if you fancied. Comes out at 3, 1. That's nice, isn't it? So basically, x equals 3 and y equals 1 is solving that simultaneous equation. Whoopee. So it says on your whiteboard, which I'm not sure if you've got one, but on a piece of paper will do. Could you try those? So pause the video. And have a go. Okay, you've unsolved it now. Well, you've solved it, not unsolved it, whatever. Here's the first answer. Did you manage it? And the second one, explain why the simultaneous equation had no solutions. Oh dear. Hopefully you mentioned something like the determinant of this thing has no inverse. Oh, sorry, the matrix, this thing has no inverse because the determinant was 0. If you remember, when we did, I was doing all that business of, okay, you've got AX equals B, and we wanted to do A inverse A, X equals A inverse a B to solve it for finding X, didn't we? Now you can't do that if you haven't got an A inverse, can you? So you can't solve those simultaneous equations, and so they don't have any solutions. Woo! And we'll get to that actually next lesson, the different sort of geometric representations when these planes don't always meet, or these lines don't meet. Right, planes. Recall the equation of a plane can be written in the form, it's the Cartesian form of an equation of a plane, something x, something y equals something. It's all come from that, what did we have? God, it was only not long ago, wasn't it? R dot n equals A dot n. Oops, an n. That was the normal vector, wasn't it? That was just any old vector. And R is your x, y, z, and that's why this thing comes up here. That becomes a constant. That's your d. And R dot n, or n dot r, gives you that bit there. Therefore, if we wish to investigate the, what do you reckon? I reckon it's intersection. Intersection, let's do it in red. Of 3 planes, we must simply need to try to solve simultaneous equations. Their three respective Cartesian equations are... Oh, let's read that again because that was rubbish. Therefore, if we wish to investigate the intersection of three planes, we would simply need to solve their three respective Cartesian equations. However, do the solutions tell us anything about the geometric positions of each plane? Ooh, indeed they do. Gosh, I bet we're gripped on that one. We consider today just the case where the three planes meet at one point. And that's about all the rest of this lesson. So what the picture will be, if you can see those lovely coloured planes there, they will all meet at just one point. So this is the case we're looking at. So what we'll find, there is just one point, so it's a unique. How do we spell unique? Apparently like that. A unique solution. The planes meet at one point. Find the point of intersection of the following three planes. So here we've got our three planes. Right, our A matrix will be a 3×3, and we'll change it into that form to start us off. So there we are, AX equals B. So all I've done is put it like that. Right, we know the tricks. We must first of all look to see if the determinant has an inverse, and to check if it has an inverse, it means the determinant must be a value, not 0. So we'll work out the determinant first for a bit of fun. It's a 3×3. You can use your calculator if you've had enough of this. So when I'm looking around for the magic machine, let me talk you through what you do. You turn him on. Oh. Menu, you want run mode. Let me just pause this a minute. I'm going to pause this a minute. Right, I'm back. So the determinant here, we said we're going to do it on the computer. Calculator. So menu, run mode. We want matrix button, so that's F3. We want a 3×3, so you put that in. And then you enter your matrix very slowly. 1, 3, -1. 2, -1. 4, -1. -3, 2. So you've got your matrix in. Ooh, you don't see it here. Once you've got your matrix in, press exit a few times. And now we want det, so determinant. So what you have to do, you have to press option. And then F2 for matrix vector, I think. And then what you need to do then, yes, that's the one. And then it's F3 for det alpha A. And it should come up. What? You don't put just det alpha A, you put det mat. So you have to put mat A. You need to put in, let me see if I can get that in the camera. Det mat A. And then it tells you it's -7. So therefore we know it's got a unique set of solutions to this. There will be an answer. Three planes will just meet in one point. Because it's the determinant isn't 0. So we know there's going to be an inverse. Now you can get the inverse on here, seeing we've already put it in. So all you have to do now is you put mat A inverse. So mat's on the F1 hopefully for you now. A to the -1. So you put in alpha A to the power -1. Never know what I'm doing here. Like that. And bingo, it comes up. Let's hope you've got the same as me, or I can't press buttons. And if you're feeling lazy like I would, I'd then put matrix B in, so you've got to go back to, oh dear, you'll have to go exit, 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 go back to your matrices on F3, matrix vector, enter in matrix B, it's a 3B1, 3 and a 1, enter in 11 minus 5 minus 12, and then you can, exit a few times again, and you can just put in then that matrix we've just dealt with. So that's, press options again to get all those matrix things back, A option and F2. So we want matrix A inverse times, gosh, not going to get that down and back on the floor, times mat B, alpha B. So you're putting in this thing. You see that? Matrix A inverse times matrix B. And then it gives me a nice one. Really nice numbers there. 1, 3, minus 1. Well, well, well. That's the answers then. That's our X, Y, and Z. So those three planes actually intersect at one point, and the coordinates of that point are 1, 3, minus 1. Fantastic. One's for you. Gosh, I bet you can't wait. So if you could pause this video and have a go at that one, and I'll flash up the answer once you're ready. So pause, please. Okay, have we unpaused? Here come the answers. Da-da-da, da-da-da. Hope you got it. Because you probably enjoyed that so much, here's another. A bit blurred. Pause, please. And here's the answer. 1 minus 1, 2. Still nice whole numbers. Okay, example 2. And what's different about this one? Yuck. It's not got numbers in, has it? In that matrix A, there's going to be some K's. So for the simultaneous equations, have one unique solution. Oh, we told it has one unique solution. We need A to have an inverse. Hence, the determinant cannot be 0. Righty-ho. So, determinant of A, if we do the square bracket, not square bracket, the straight brackets, and we write A out, it will be 2, 1, 3, 1, minus 2, and here we've got K plus 1. Here we've got K, got 4, we've got a 2. Right, if you wanted to do determinant of that on your calculator, you'd be sadly upset because it won't like K plus 1 and it won't like a K there. So you could expand it all and have lots of fun, or you can do a bit of factorising to try and make that matrix something easier to find the determinant of. So what I'm going to do here is I'm going to do column 1, take 2 lots of column 2. Now, why have I done that? Well, I'll show you. If we do that, that'll be 2 lots of that away from that be 0. That's a nicety. 2 lots of that, take it away from 1 and you get 5. Not so great, but never mind. And that will become k take 8. And leave all the other columns alone. There are other ways to do this, but this is just the way I've done it. Now I'll do a little bit more. I'll follow the same sort of pattern and I'll do column 3, take away 3 lots of column 2. So this is the same as the determinant of this thing. So these 2 columns are staying the same. But this one now had 3 of them taken away, so you get 0 there. You'll get k plus 7, and we'll have minus 10 here. Now it's a little better to do. Determinant of that, so the only middle one we're going to do is that. And remember that's a minus when you write it out, so it'd be minus 1 times the determinant of this 2 by 2. If you take that out and that out, we're left with 5k plus 7 and k minus 8 in there and a minus 10. That's a 2 by 2 matrix, and we're happy to expand that. So I just need a bit more space. I'll go over to the next slide. Oh, look, there is part of the question. Then what did it say? Solve the simultaneous equation has a unique, find the possible values of k. Then taking k to be 1, solve these simultaneous equations. Okay, all right. Right. A bit more info. Oops. Right, let's see. So we were expanding that 2 by 2 out. So we had minus 1. If we expand that matrix there, we've got that takes, so 5 times minus 10 is minus 50. Take away those 2 things, k plus 7 times k minus 8. What does that come out to be as a determinant? Remember, take the minus through, so we've got 50 plus, would it be plus, minus, minus? Yes, it would be plus. If we expand those 2 out, we'll get k squared minus 7 times 8. Well, you know, is 56. Oh, come on, mister. Hello, Poppy. 56. And I was doing that in a funny order, wasn't I? 7k and minus 8 just gives you minus k, doesn't it? And if we sort that out, we're going to get k squared. Hello, Poppy. Minus k minus 6. And that actually factorizes, doesn't it? To k minus 3 and k plus 2. Nice numbers. So therefore, if we were having the determinant being 0, the determinant would be 0 if k was 3 or k was minus 2. So k can be anything it wants to be, any integers you like. Any integer except 3 or minus 2. Because if it was 3 or minus 2, the determinant would be 0 and there'd be no inverse. Right, the question then said, if we let k be 1, what happens? What is x? What is solve the simultaneous equations? So we'd then put this in our calculator and check it gives us a determinant, which it does. We might put this in as, this was what it equaled. I can't flash back at the question or I lose a thing, but it was 5, 2 and 8. So popping this in your machine, you might as well just put it in. So if you put that in as matrix A, that in as matrix B, and then you put mat A, so in your calculator you'd have to put mat A inverse times mat B, add that in when you've got the A and the B in, and it actually comes out as minus 4, 1 and 4. Have a go and check that. That's a solution. If you want coordinates, you'd write them as that. Wonderful. Right, can you do a similar thing with this question? So very similar. Find the values of k for which it can't be a unique solution. And then take k to be 1 to find out what it will be if you use k as 1. So pause the video. Have a go. There you go. There's the answer. Hopefully we're ready for that. So I did a bit of fiddling with the matrix in order to get it down to something I could expand out. You could have done it anyway, but I've used the 5, 0, 0, so I did 5 times that matrix there in that corner, which gave me that. So there's only a 0 solution when k is 7. So if you had k as 7, this wouldn't have a unique solution at all. Something else had happened that we'll find out about next lesson. So as long as k is not 7, you'll have a unique solution. Told you to use k as 1. If you use k as 1, use your calculator for finding A inverse and this. It comes out as that rather nasty looking answer because there was an R there. Fun. Okay, this is a bit of extra, but it's really good fun. Have a pause of this now and go to this link here. I'll put it on your homework sheet and watch the funny man doing his bit. And he introduces something called Cramer rule, which I think is really interesting. You might not. It says what Cramer rule does. In linear algebra, Cramer rule is an explicit formula for the solution of linear equations with as many equations as unknowns, valid only when the system has a unique solution. It works as shown below and is named after Gabriel Cramer, who was around in 1704 to 1752, who published the rule as an arbitrary number of unknowns in that year. Although Colin Maclaurin also published special cases of it in 1748. So it's one robbing from another again. These naughty mathematicians were always fighting who solved what. Right, hopefully, please pause and watch his video because it's really good. And it brings out what this Cramer rule is. So he would be, if you've watched it now, which I advise you, here is your system of simultaneous equations. This is the Cramer rule for it. We've taken D as what we were calling A before. That's the matrix there. The answer to this solution, that's our B, is 3, 0, 0. Now it calls dx, if you've watched the video, dx is the coefficient determinant. Basically, it's the same as this one, but replace the x column with the 3, 0, 0. Right, if you were to find the determinant of D, you can put it in your calculator, you'll get 3. If you were to find the determinant of dx, I am in the way. Oh, so if you find the determinant of that one, I think I've written this down anywhere. Oh dear, I'm in the way and I can't see it. But basically, then you do the determinant of that divided by the determinant of that. That must have been 3 as well. So it was 3 divided by 3, and it gives you 1. So that's the value of x. And you can do similar for finding the y and the z. So you replace that column there with that. So you'd have this matrix. If you have to y, replace it, put the 3, 0, 0 in the y column. And if you found the determinant of what we call dy, and then you do dy divided by that 3 there from D, you'll get the value of y. And the value of z in a similar way. You replace this column there for Z with the 3, 0, 0, find DZ, and then do DZ divided by D, the 3, and you'll get the value for Z. Nice little one that. That's a bit of an extension, not on our syllabus, but it is good fun, and it should be probably seen at university. I'll let you have a go at one now. So here's one. If you understood that and you've watched the video, have a go with this one. So please pause video and have a go. Oh, I'm meant to be out very soon. Oh dear. Right, so hopefully you've unpaused now. There's the exercise for later. You'll enjoy that. Here's the answers. So I found the determinant of D, dx, dy, and dz. I just replace the 4, 3, 9. As you can see, put it in the x column, put it in the y column, then put it in the z column. Got those determinants, and then you can find x by doing 35 divided by 7, minus 7 divided by 7, and 14 divided by 7, and you get the answers. 7 minus 1, 2. And this works however big you want that matrix. You could have, as long as you've got, if you had 10 equations, and you have to have 10 unknowns, and by 10 matrix, this would work. You could find 10 letters. So what a brilliant little thing from Kramer, or whoever he nicked it from. Right, so I'm leaving you now. Hope you enjoy this exercise, which is up here, and I will see you for lesson 4. Hope you're all well and enjoying life as well as maths. Okay, bye bye for now.